Hi, everybody. Don't see much of you. Let's see. Let me type some messages. We start at 10:45. So we're just chilling out. I roll. Questions to the chat. In default, your mic is muted, and yeah, it's not. If you all start talking simultaneously, the bandwidth would be exceeded. Questions to the chart. If emergency, unmute yourself, speak up, got the response, mute yourself. Good. What would be possible emergency? The experience shows already that it's when a presenter could not follow the chat, forgot to look into it, and doesn't answer your question. Your question is not answered for a long time. If you put questions to the chat, make sure that you post it to everybody and not privately to the teacher, because your questions are useful for everybody. Strange enough, I don't see my window. Let me check my window. It's not very convenient interface. Can you hear me, Rule? Why don't you type something to the chat if you're present? Excellent, very good. So our presentation will be given by Yanis. We're just waiting for him. I don't see him at the moment. There are at the moment 3 participants except me. There will be homework session on quantum transport, homework package 1, traditional question, perhaps a little bit personal. Who of you tried to make homework? Type yes if you did so. Type yes in chat if you attempted one. Right, I don't have more answers, sir. At least Rule has tried to do homework. Did you make much, Rule? Hi, Yanis. Stuck at number 4. Yanis, do you see chat window? Hi, Yanis, can you hear me?
Yes, I can.
All right, very good. Because you kind of keep silent.
Oh yeah, I couldn't hear you. My volume was turned down. I thought, what's happening?
All right, that was a simple solution.
Yes.
It's strange that most of students, I just made a survey recently, like 90 are completely satisfied with Zoom.
Wow.
Didn't have any difficulty to connect. Yeah, I did have a difficulty to connect. I managed, but that's probably generation difference.
Yeah. No, but some software is really bad. I mean, Skype sometimes can have issues disconnecting.
Yeah, but that's kind of
It's good to know that they could establish a connection.
Let's see. It's still time. How many participants do we have?
6.
No,
no, five.
5, except you and me. Right. Shall I focus on you?
Yeah.
Right. So it's called Spotlight Video. Perhaps you already can share your screen and we see what will happen there.
No, I cannot share because you are sharing. You need to disable this.
Yeah, Spotlight Video. And then okay, I will stop share.
Okay.
Try to share your screen.
So let's see if it works. I don't see one application. Okay, we share the screen then.
Okay, there's option to share an individual window.
Yeah, but it didn't appear it. Probably because I started the window from terminal.
Anyway, you can see what Jan shows to us. Charge transport statistics. So it's a first problem of the first package.
Yes.
And how many problems are there in the package?
3.
All right.
But how can I get it full screen?
Perhaps you don't have to, at least. What are reactions of the students?
What?
I wonder if students said something.
Oh, no, I didn't hear anything.
Did you see the chart?
No. Let's look on it. Oh, there is something. Raise your hand. Okay.
Yeah, that's a disadvantage of sharing the screen rather than window. So you do see chart.
No, haven't found the chat. I cannot move it there. Okay, let's stop the share. Desktop 2. Okay, if I do this. Oh, it's better, I think.
I see what you see, but it's still full screen.
Yeah. So it only has a title bar. That seems nice. Right. So now I need to find the chat.
There's kind of a menu which pops up if you move your mouse to the
yes, I found it.
lower end of your screen.
Okay.
Upper end.
I found the chat. Okay.
Good.
I can put it on one screen and the other presentation, other one. Okay. Okay. Right. I actually got it this application on the tablet running, so now I can write quite fast, I guess.
Oh, all right. Very good.
Yes.
And can you write what you write? Sometimes it's important.
Yeah. There's a button here. Yes. I can change color. Which one I want? I guess this one would be. No, it's dark. I cannot see in my tablet. Only white ones. Okay, this is going to good.
Good. So we will start in a minute. Yanis, it's your floor.
Yes.
Just I would ask everybody to type into chat something like "okay," and we will see what happens. All right. Now we feel the presence of student, at least one student so far.
Yes.
2 students. 3.
Good. Yeah.
Okay.
Yes, fine.
3 students at the moment. So perhaps you can start with questions and all right, that's all right. It's your floor.
Okay.
Just understand how far they are with homework.
Yeah.
Good. So
sure.
I unmute myself.
Okay. So hello everyone. My name is Yanis Edmonds, and I work at the ULEAD group as he works there for the 3rd year. And I'm also giving these problem solving sessions of quantum transport course. The purpose of these sessions is to help you to solve these problems which are not very which takes time to get used to, and even I myself get to needs some time to review the material before the lecture, we have to start showing these problems to you. So usually I can start with asking you whether you have already had looked on the problems. Perhaps you can type in the chat or say no. So I know that you have looked into it, or perhaps you have immediate questions. Okay, that's actually, oh, okay. Okay, right. yeah, this is actually, yeah, since you already, the chat puts your name in there, that's kind of discouraging to put your answer. But yeah, it's usually the case that the students are, from the last years, that students try to look on the problems but really don't solve them, or yeah, kind of thing. But some students, capable students, actually can solve the problem and ask very good questions. That's it's sometimes encouraging. Anyway, you have plenty of time to get used to these problems, and I will overview the three problems in this problem solving session. So the three problems are related to the charge transport, and these are actually the basic ones which one needs. These are the basic ones which one needs to master, and some elements of the second and third exercise that constantly appeared in the exam, which is of course more complicated in a sense that you need to understand more concepts. Okay, let's start with the first one, the first problem. So, charge transport statistics. The thing which we look into this, but what we are considering is a simple system. When you have a single scattering region, and you have some voltage bias, and this is voltage bias. Due to this voltage bias, you would have some current. You also always want to know the current, and not only you would get a current, you can also get charge fluctuations in time, which also gives valuable information about the scattering region. So for the scattering region to characterize the scattering region, we need to understand what happens to different channels. And the channel is something which is quantized leads. So we know that due to the transverse quantization, we can have multiple different modes at the lead, multi-transfer of modes of lead, which forms a channel. And this kind of modes, which are, let's say, characterized by P, have different behavior with respect to scattering region. So okay, let's look on the basic formulas. And so the basic formula is this Levitau's formula, which we're going to use in this exercise. In the book, it was not derived, but it was kind of shown from the special cases that it's true. And in this exercise, we actually going to do so the book pulled this formula from a special cases, but not really proved it. And in this exercise, we're going to go in opposite direction, taking this formula and looking on proving the specific properties of this formula, trying to show that it corresponds to the special cases which we know how to derive. So to understand the formula, so we have some integral over energy. We have a sum over, I don't know what happens. We have sum over channels. And everything is under a logarithm. And under the logarithm, we have 1 plus Tp, that is eigenvalues of the scattering region, e to I chi, where chi is some arbitrary the parameter which gives this characteristic function. So the lambda of chi is called the characteristic function in statistics. So FL, the Fermi distributions, and yeah, and so it looks a little bit long, but it's actually pretty simple. Is this formula, why, what is this big capital lambda is, it allows us to evaluate the statistics. And so the statistics meaning that we can evaluate the charge as function of time for different kind of a fluctuation. Sorry, not charge as function of time, but yeah, fluctuations as function of time. And for that, we just take the derivative of the capital lambda with respect to I chi. And when we do the derivative, we set chi to 0, and we are totally getting the specific cumulatant of the thing. With this cumulatant, the special thing is a second order cumulatant, and it's related to a noise. And the noise is related to a Fano factor. So yeah, so and the Fano factor is something which characterize since it is some dimensionless quantities that characterize noise in the system. Let's see. Okay, now we have reviewed the formulas. We can start using them for to answer some questions. So let's start with proving that we can get a current, that we can get a Landauer formula from this Levital formula. So to do that, we need to find the first derivative of the Q, and this first derivative to give us some space, make it the manipulation is easier. Let's rewrite the Landauer formula as follows and introduce this GP, which contains this this L1 plus TP and yeah, this long expression. And so we can now take the derivative of this logarithm of this lambda logarithm of lambda to get a charge, and see. So we get Q is e to the logarithm lambda of the IK, and now we need to derive it. So what we can do is, we plug this logarithm lambda inside. So we need the logarithm lambda IK is what? It is dE 2 pi over h to s delta t, sorry, and sum over the channels, and taking the derivative as the logarithm of gp gives us gp in the denominator and gp prime, which were both evaluated at chi is 0. And so when we evaluate gp at 0, we get 1. We take derivative of gp. It gives us, with respect to ik, it gives us dp eik. So let's be consistent. Let's plug in immediately the value inside. F left 1 minus f right plus dp dp f right 1 minus f left, and we see we have common factors, and in the end we get that gp prime is d prime f left minus f right, and that's then plugging that inside here. We get to prove that we can obtain the Landauer formula. So yeah, that was simple. And right, let's now move some more complex stuff. So now the second question is about deriving the noise, and noise was related to the second cumulatant of the charge, which let's now going to derive. Perhaps I can reduce it's a bit sick. Okay, this seems better. So like, again, we need to take derivative of the GP, but this time we need to have a second derivative. So let's do it. dt ln lambda dik square. So first we do one derivative. And that di chi gives us from the previous expression so let's do it a bit differently. So to get this derivative, we plug in the expression, the constants, our integral, the sum, and now what we need to do to get this second derivative was logarithm gp di chi squared. And right, now we need only the second derivative gp. So the first derivative we might look on the slide before. Fortunately, I have the paper for me in front of me. So the first derivative, well, is d pi e I chi f left one minus f right plus dp minus dp because of the chi minus dp e minus I chi f right minus f left. So that was the first derivative. We need a second one also. Double dot. Okay, so it's again rather simple. dp e I chi f left 1 minus fr minus plus dp e minus I chi f right 1 minus f left. And now to express the derivative, let's di chi gives us di chi g prime dot g prime because it's logarithm. Now we need to do the mass and take the derivative again. We take the up part first, and we as well might do the derivative of the second term. And right, now we need to plug in. These things need to be evaluated at chi 0. We already know that at chi 0, gp is 0. So, sorry, gp at 0 is 1. So we can forget about the denominator. Oh crap, now this is nice. And now we can forget about this exponent. We can put t pi prime in front of all expressions and just focus on the Fermi coefficients plus f right minus f left. And now the second part, this comes as minus f left 1 minus f right plus f right 1 minus f left, and okay, this seems to cancel each other, and it gives us making mistakes. Oh, okay. I forgot that I had to take the square of the GP prime. Right, I need to do it again. Can I move it? So we agreed that we need to calculate G prime dot minus G prime dot square. Okay, so we get, again, let's forget about T prime because it's all common. F left 1 minus F right. One minus F left. No. Plus. No, now the square. Oh. Sorry. We actually, since we do make a square, it's actually important what coefficient we have. Wait. No, sorry, not important. No, so. Oh yeah, so this one is independent of t, so it's always 1. So yeah, if you look on the result, yes. Okay, this is complex. Right, minus t by p square, f left by minus f right, minus f right 1 minus 1 f left, this v square. Yeah, the question is, where's this? Look on the answer. No. Yeah. How this 1 comes in? So this part, the first part, is actually corresponds to this minus. Now there is this trick. So it might looks like so it looks kind of that the first part of the result is quite similar to this part. So this looks quite similar, but now the catch is that in the result we have f left 1 minus f left, which are separated, but here we have f left 1 minus f right, and to get to this final form of the result, which has benefits of giving us information about what happens at t pi when the transmission channels are really transmissive, that the eigenvalues of t are close to 1. When they are close to 0, that's the benefit of writing this the result in this form. Right. Now we need to continue. So I guess we can start with the second part of the expression. F left 1 minus f right minus f right 1 minus f left squared. Let's process what happens under the square first. F left minus f left f right minus f right plus f left f right, which is nice. So we get something simpler. So we need to square only f left minus f right squared. Which is part of the formula as we saw. So this gives us minus tp squared. So this term plus this term. So we have proved. Now we get to now the question how to add this one inside for this expression, and to do that so we look on this f left minus f right was f right 1 minus f left. Two. Right, and what we can do is we can write what we want. No, let's first expand it. It's equal f left minus f left, f right, plus f right, and again the second part. And right. To get it on the second form, no crap, what happened? Ooh.
Yanis, we have a problem. Are you taking care of this?
Yeah, my device restarted and then no way. Okay, we'll get it back soon.
Sleep.
Yes.
Is it for us? Oh, okay, not for us. Okay, good.
Yes, sorry. Yeah, okay, so the screen is still on? Okay, so you will see the derivation in the problem solving and the solution manual. It's a little bit hard to write it as annotation, but the thing is, so we already have proved the essentials, and so we actually can prove this formula from the elements I gave you. So let's now look on the at the equilibrium noise. So for that kind of thing, we only need to say that the left reservoir and right reservoir Fermi functions are equal. Let's say it's 1/1 plus e to e k belt Boltzmann t. And we can use the expression we derived in the previous slide and plug it in, just plug it in. And again, the derivation is a little bit involved, but sorry about time. When we plug it in, and essential property uses so we first plug it in and then use properties of the Fermi functions. For example, 1 minus f Fermi function is equal to what it equals. It equals to think Fermi function of minus E, something like that. For example, properties, but the essential property is so we plug it in, we expand the brackets. Yeah, that's basically it. I don't have much time, sorry. So we go, so that would give us a noise. And that would be, the previous slide would give the noise at the equilibrium. And now let's derive the noise when we apply voltage bias. And if you apply voltage bias, which is much larger than K pulse minus T, we can treat it as the Fermi function as a step function. And it's convenient to treat the step function symmetrically. So we add EV minus EV to one side and plus EV to other side, and plug it in again as the same formula, and do the algebra with a set of functions, and which allows us to obtain the the final expression. And that's basically it. For this question. The next question is about Fano factor. And the Fano factor for a kind of specific problem. Let's say, so the question is, how can we the Fano factor let's say we have multiple levels. Let's say we have two channel system, and that's our model, that we have two channels, and let's say we measure a noise and we measure the current. So the question is whether we can get some valuable information about these two channels, and the answer is yes. So now that we can express the current with the Landover formula, and we can express the noise with the formula which we derived in the previous slide. And plugging them both inside, here we see that for Fano factor, we obtain a formula. And to use this formula, to show how to use this formula, let's say we have non-conductance, we know non-Fano factor from some experiment or any other one, and that allows us to form a system, and the system we can solve simply as a quadratic equation. So let's write it properly. So 0.59 is equal to some P1 minus T prime sum over TP, and the sum we know that is equal to 0.5 where P is, because we have two levels, we have it's 1 and 2. So this we can solve and obtain the solution to this equation. So let's have a break for 5 minutes until I prepare for the next exercise. So great.
While if anybody is here, I would like to put a link to survey about Zoom, about your personal experience with Zoom. How easy, how difficult was that? What were suggestions on improving Zoom presentations? So I posted a link to the chat.
Oh, so these are not delta functions, these are theta functions. And so you know that, hopefully everyone can hear me. So you know that since the Fermi function is kind of goes from 0 to 1 with some special at some specific energy, when we decrease the temperature as low as possible, then this step becomes with such narrow width that it becomes a theta function. Okay, so I guess since no other questions, yeah, it's very hard to present this way, but let's move on the second problem.
Look into the chat, Yanis.
Chat, yes, I see. Okay, I see. But why is the EV? The EV over 2 was because we assume that we have a voltage bias from the left lead to the right lead, and we might so one way is to say that we might have one way is to symmetrize this delta V. So what's important is what is the difference between the energies as Fermi functions we can actually hopefully. So we know what is important is actually this picture. When we have F left, we have F right, and yeah, and the F left minus F right is some voltage bias. That's how voltage is defined, and the energy is actually the zero of the energy is actually kind of arbitrary, and since we should be able to shift the energy without any consequences, it's also convenient to choose the voltage bias to be symmetrical. So if one would say that F left of energy is theta of energy and F right of energy is theta of energy plus EV, one should get the same result. And the reason for that is when one does this algebraic manipulations, is what matters is actually the width of the width of this the step. When one does these manipulations, when so it's one needs to substitute these things inside, and then one will get the feeling why we can't have any voltage shift here. So it's a good question. So thank you. It doesn't. Yeah. Okay. Let's see. Yeah, I think so. Yeah. So the picture is misleading. Let's opposite. Yes. Yes. The energy on the left is larger than the right on the right. Okay, shall we continue? Okay. The second problem, the one of the which, yeah, unfortunately, the one which takes the most, going to take probably the most time, is Aharonow's Bohr ring. And the setup is simple, is that we have two scattering regions and the arms of scattering regions. These are here and here are symmetric, and between these arms are magnetic field. So when electron goes from one arm to another arm, it can acquire two kinds of phases. One is a dynamical phase, which comes due to for example, electric field, changing the energy of the electron or something. Another one is a magnetic phase, sorry, geometric phase, which is here, which only is acquired when one makes a pull, this electron makes a pull loop around the magnetic field. And if it goes back and forth, then this acquired phase is zero. And right, between these two arms, we have magnetic flux, and again, one is interested in understanding what is this, what is the characteristics of this scattering region. So this full thing we can just treat as a generally it's some scattering region S. And to understand any S, we need to understand what is eigenvalue, what is this? It's three transmission eigenvalue, for example, or yeah. And that's what we're going to do with this exercise. We try to understand what is the amplitude if the electron is on the left, go to the second arm too. Right. Yes, that's also the transmission probability between terminals. Right. So the simple thing is to ignore our back internal reflections, and that we can do by just considering two different trajectories. So let's say our T0 is trajectory which goes around the link from the up, and the other trajectory which goes from the lower part. And to sum it, so So the first trajectory, we need to first do go the arm. So it needs to be transmitted from the first arm to the, let's say, to the other arm, which in this case is symmetric, so we don't need to note it. When it goes here, the electron goes to the second arm, so it acquires this phase factor. We add it, and then it goes outside, and again it needs to be transmitted. And the same is true for the other arm. We have T E2 I Chi2 plus Phi2, and again it's transmitted. So that explains the result. Let's look on a more sophisticated problem. Let's consider round trips. So a round trip is something which, let's say, we have this ring, and electron entering can enter to the up, and there are different things which it can do. It can do scattering like this and exit from the up. What else it can do? And this we call a round trip. So it can also go from the up, and it can go all the way and exit from the upper arm. And what else it can do? It can by just entering the upper arm, we can have it going this way, and then it going outside like that. That's the third option, and it's sometimes hard to imagine what the fourth option is, and it is let's see. Okay, so it is like that, I guess. Yeah, and we call these two together to kind of distinguish them from others. Let's call them T up, meaning that this is trajectory where the electron enters the upper arm first, and it, as we see, it exits the from the upper arm. So let's call it T up, and let's note that it's single round trip. So we add index 1. The second option is the second trajectory is that the electron enters an upper arm first, and it exits the lower arm. So we call it up down. And again, a single round trip gives us what we needed. So yes, so now we just need to evaluate. We have picture representation for this T up 1, T up down. We already know that T up, since we from the the conditions of the problem, we say that the electron enters the upper arm. No, sorry. The electron, and if the electron enters the upper arm, then there is no probability that it will go outside from the lower arm. So that's what it is meant here. But yeah, so on this one, that it is already that it goes in up to the upper arm, and then the upper arm is this one. So this is a trajectory that follows. Right, so now we can simply just write formulas without any issues. So first we need to be transmitted for the electron, and it acquires a phase factor EI chi1 plus phi 1. Then it is reflected. When it is reflected, it acquires phase factor I chi1 minus phi 1. Again, it is reflected on E I chi1 plus phi 1. And then it is transmitted, exits. And the second part, the second trajectory is first it is transmitted. Again, we acquire chi1 plus phi 1. It is transmitted from the upper arm to lower arm. So that's the difference from the previous case. And now we acquire the phase factor I chi2 plus phi 2. And again, we are getting transmitted and acquire the phase factor EI chi1 plus phi 1. And the last part is to get again transmitted. So that is the answer. I won't write the second up and down part as it's since the first part is already illuminated the concept. So now let's look on what we have done. We have done this, we did this, we did this. In a sense, we did this one. And now let's focus on these trajectories. Let's now introduce more abstractions through the trajectories. Let's say the trajectory, if it goes like this, is equal to so is equal to a trajectory which goes like from the up plus a circle. And let's again let's add another thing. Let's say we have a trajectory which goes like this. It's equal to trajectory which goes like, which is simple sorry. times this trajectory times the trajectory which makes a following round trip. And the other kind of trajectory which we have in the up-down part here, we could as well do some abstraction. And say, need to look in my notes. So this one, can we do in subtraction? Right. On this one, we cannot so easily abstract. We can do something like writing it but it has a discontinuity here. But what's important is this internal part, this the round trip, and the same for the other kind of trajectory. That helps us understand. So, for example, if we now we can write the trajectory t up 2, and we can start with simply starting with a trajectory which says that we exit the ring from the upper arm. So between these things, what will happen is we are able just to add a round trip plus or this kind of round trip where we go around full ring. And on the other hand, it's possible that we might have a trajectory t up down, that meaning with a single round trip, the electron from the upper arm exits from the lower arm. So we might add round trips which have a form as follows, and that allows the trajectory which originally exit with a single round trip exited from the lower arm to exit from the upper arm. And there are two ways how it can do that. Right. So, and this multi-trajectories, we know the formulas, and actually these are the formulas which are written. So this is reflected. This is actually this. And the same is for other trajectories. And so it's quite usual on the reverse. So we can obtain T up. And what's interesting is that the specific need for 1 or 2 on the left was not necessary. What we needed only is that the left side is 1 round trip more than the right, the terms on the right side. So we have obtained a recursion relation, and which we can write as follows. So here we have n round trips terms, and on the left side we have n plus 1 round trip terms. We can do the algebraic simplification, and so we get a nice formula which relates n's round trip terms to n plus 1. The question now is, so we have obtained the recursion relation. How can we use it to obtain the solution? And that can be done we say that, so we might use these recursion relations together with initial condition. Let's say we have assumed that the electron, we might assume that the electron enters the upper arm first, then we can just do it multiple times and obtain the probability of the electron going outside with n turns. That's nice, and we can rewrite it in a matrix form. And let's call this matrix Q, I guess. Yes, let's call this matrix Q. And so we have the equation T up, T up, down, n plus 1, meaning that's index for it. And it's equal to Q times T up, T up, down, and is n round trips. So by just applying this Q multiple times, we are able to understand the probability of the electron entering with a certain number of round trips. And let's now do the nice trick, and let's sum over all these trajectories. And to do that, we introduce the sum of amplitudes. T up and T up down. Now, to get the equation for the sum of the amplitudes, we shall use a following trick. Uh, mm, the idea is so T up up, T up down is a sum over n, T up up n, T up down n. And we know that we can express it as still n q yes, qt up up n and t up down n minus 1 and no, sorry. What we do is we separate the 0 element of the sum. And we can write it as t up 0, t up down 0. And now we do the summation starting from the 1. T up n, T up down n. And to get, we now want to get to the sum of n is 0, because that's how t is defined. T up 0, T up down 0 plus, and here comes the trick. We make a shift from 0 and so we make shift of n, and to make it more obvious, we instead shift n down n plus 1 in this way, and t up 0, t up down 0, so gives is q times n, t up n, t up down n. And that's we recognize the second term as being this t up and t up down, and we have obtained the equation for linear equation for the amplitudes initial condition here, and the sum of all amplitudes with all kinds of round trips. So now we can, in principle, use a formula what is 1.4. So that gives us this equation for the sum. Okay, so now we can put, yeah, the identity minus q is equal to initial conditions on the right. And right, that. And the initial condition is that So this particular initial condition would give us amplitude, all amplitudes, the sum of all amplitudes which only had entered from in the upper arm first. So that's in to consider the full case, we just would symmetrically deduce that we can add the second part. So let's say we want to know where amplitudes when the electron enters the lower arm first. Then we do the same kind of derivation. One can convince it's himself, and instead add the initial condition at the lower part. And now what we are interested is actually the sum over when an electron enters the lower arm and when an electron enters the upper arm first. And we can sum the equations. We have the same Q, and right, and this is it. So this is the equation, and this is the probability for electron going from left to right. So it's, yeah, done. In the book, it's, so this is a method where we count all trajectories one by one. It's also possible to count the amplitudes. That's what we're going to do the next exercise. And in certain situations, counting trajectories is simpler, and in other situations, counting the amplitude is simpler. The difference lies in the fact if you can count the all trajectories, you can immediately write the formula for full amplitude when one practices it more. Where for the amplitude, one needs to always solve a linear system, and that sometimes can be a more daunting task. When, for example, when the matrix becomes 4 times 4, but when you just want to know a specific kind of amplitude from one arm to another arm without without needing to calculate other amplitudes. So that's why we consider also this method. And in the book, Quantum Transport book, one can see how the Aharonov-Bohm ring is considered by counting the amplitudes. So let's have a 5-minute break again, as previously, and ask questions. We'll type it here. And yeah. Okay, so I'm back, and let's now look on the last problem. And the last problem, for the last problem, we have about 15 minutes or so. Let's take a bit longer because we have these little breaks, and it's actually a bit stressful. So let's take it for 20-25 minutes. And technology is again not working with me. Okay, partial probability amplitude. The system of this problem, there are two systems in the problem. The one is just you have simple scattering region here, and for the scattering region, we just want to know what is the probability. We know that we have some dynamical phase factor, and we want to know how to consider this single scattering region as a single one. So, and to do that, we're going to look on the particular trajectories. Since we have now backscattering, it's not necessary to write a system of equations or anything. like that. In the second problem, second system is B, and it's much more complex. That has dynamical phases, like have these scattering regions here. It has this symmetric scatter in the middle. And to consider that problem, we are going to employ the second method for describing the amplitudes. It's by writing the equations for the amplitudes, and not just by counting the trajectories. So let's see. We can now look on the scattering matrix. So we have 4 elements. The T1 prime, let's start with this one. So it's going from the left to the right. That means we get a dynamical phase, I gamma 1, times a transmission coefficient, which for the which for the left side is happened to be T prime, and R1 prime, meaning that the trajectory is what? The arrows are on the same side. That's the trajectory enters from the left and goes back to the right. So we have E I gamma 1 times R prime E I gamma 1. Yeah, and that's it. And for this T1, what we have is now we're going from the left to the right. That means that we're going to have T instead of T prime, and D times E I gamma 1. The one is R1 is just R, but it's a bit misleading picture, meaning that it scatters back at this. This is R1. So we can write it together and obtain the scattering matrix S1. So that gives us a solution for this question. The second question now is to give the amplitude for trajectory which goes from the branch 1, that's here, to the branch 2, so here. So let's now, without any internal reflections. So what we can do, in this problem, there were 2 explained trajectories, the path A. This is the path A. For the path A, we have what? First, we need to have transmission here times E I gamma 1 times S1 2 times E I gamma 2. And the last thing is we need to, oh shit. So last thing is the last thing is we need to be transmitted through the scattering region, so we add these there. All right, this corresponds to T prime, sorry. That's space path A. Now path B is as follows. We start with branch 1 and we enter the branch 3. Let's see if I can. Oh, since the colors are different, it's visible for you. And so we go this way. Now to get this amplitude, we need to first get transmitted. This is gives T times EI gamma 1 times S13 in this case. And EI gamma 3 R prime, EI gamma 3. Again, now we need to go from 3 to 2. And EI gamma 2. O and T prime to exit the thing. So this part corresponds to this. Okay, so, and this gives us the expression for pass B. So yeah, this I think this problem needs also to include more complex trajectories. So we have, what we can have here is, let's see if we have a picture. No, we can actually have a backscattering in here. And now to consider it, the backscattering is happening because, why? We have reflection here, L prime, and we have what? We have S33 element here. So this is what makes a backscattering here. And it's simple to say that the backscattering is simply multiplication with S33 times E2I gamma 3 times R prime. And n, let's say n, and we can just multiply this simple trajectory with this backscattering in n times to get the result which we want. Right, so that gives us some simplicity, and here we can use it. I have emphasized it here. This is a single, this is square, and the nice thing is that if we add 1 plus e to I to I gamma 3 R prime S33 plus e to 2I gamma 3 R prime S33 square, and so. But we know from the mathematical expansion that expansion 1 minus x is 1 plus x squared plus etc. So we can simply, if x is smaller than 1, which is true in this case, we can see e to the something is 1, the length of 1, and R prime S33 is strictly smaller than 1. So we are allowed simply to write it as 1 minus e to I gamma 3 R prime S33. And now we can just sum up the path A and path B to obtain the result which we want, the total amplitude. And this total amplitude, however, also with some paths are path B, it's not a true amplitude. And the reason being that we can't have backscattering here, we can have backscattering here, And we can have also something like a scattering, which kind of makes system which goes around the system on one direction, another direction. And actually, the first problem, when I inherited it, it was solved with summing the trajectories, but at some point, summing the trajectories, the reasonings become so difficult that sometimes you might ask yourself whether there is a solution is the solution you have. So let's now turn to the last question of this problem, the one which will give us the amplitude from going to the first arm and exiting the second arm with confidence. So let's start. We introduce these amplitudes from this scatterer. So we have exiting amplitude B and incoming amplitude. And what we're going to do is to write a relation between exiting amplitude and incoming amplitude. So a simple thing is say that if we have exiting amplitude, to obtain the result from first to second arm, if B is calculated, assuming that electron enters only from the left, then we can say that to get from the exiting amplitude B2 to the amplitude at the 2, we multiply it with the phase dynamical phase factor EI gamma 2, and then we go through the system with T prime and multiply with B2, which is its amplitude, exiting amplitude. So now the question is, we need to find this one. So how can we do it? We do it simply. So first we write all relationships between A and B. So for A, here's the thing. For A, what we might have exiting amplitude B, and this 2I gamma 2 is due to, so we have this B1, and what we can have it coming back. But we also actually can have electron coming from the left arm to the first arm. So we have two contributions, two terms in the sum. So this is the condition that electron comes from the arm 2. And that forms the opposite terms formed on incoming amplitude A1, A2, and A3. From the incoming amplitudes, we know the definition of the scattering matrix is if we have incoming amplitudes, we can get outgoing amplitudes by simply applying the scattering matrix. And so now the last part is just to get an equation for B. So let's write A is equal to R prime ET gamma 1, R prime E2I gamma 2, prime E2I gamma 3, vector B, and plus, let's call vector T. And vector T is T prime E I gamma 1 0 0, meaning that electron enters the left arm first. Let's call this one R. So what we have is A is RB plus T. We can substitute B. So we want to B. So let's substitute B here. We obtain A is RS times A plus T. And that gives us that A can be expressed identity minus, sorry, it's identity minus RS, A is equal to T. So A is simply an inverse minus 1 T, and B, so plugging this in here, we get to the formula, the final formula, and that then is, that was the last question of this this problem, and the last problem, and what's the last question of overall of the last. So with that we can finish our solving session.
All right, thank you, Yanis. Let us see.
Yes.
I wonder how many of you. Oh, sorry, Yanis, there are still questions.
Okay. Whether the R and S order of S matter here. So yeah, I don't know if it's a typo problem for me now. It seems that R needs to be the left of the S. I guess it matters. It's just a typo in the presentation.
Let's see, it's just
the
matrices or the vectors.
Yeah.
What? Just
yeah, R is matrix. So I guess
R matrix.
Yes.
Okay. Them it matters. You just.
But there is actually a case.
Vector notations.
No, the case is that we have identity minus S. Wait. R S minus 1 T. And the question is whether it's equal to this thing. Maybe.
Well, can't come from general reasoning. I believe it does. If those are matrices, the answer depends on order of multiplication.
No, but actually, this. But if S is unit, yeah, maybe I don't know.
It must be. Anyway, thank you for staying with us. I just wonder how many of you can still type in chat. Has any people ability to type into the chat?
Oh, okay. That's excellent. Okay.
Okay, that's it. Anyway, we just training our presentation skills. Of course, there's a new system. We will improve. There will be a lecture on Friday, I believe. Also will be given in this manner. If you have not filled in the form, I posted a survey about your experience with Zoom. If you haven't answered, please answer it. It's useful for everybody. It is all department is now collecting the responses. There was perhaps from somebody of you who had a problem connecting on Apple laptop. Anybody of you connecting Apple? All right. So this person.
Well, probably it's a kind of interesting question, because if they have a problem connecting with Apple laptops, then probably they are not here.
Well, surprisingly, was answered the question in a systematic way. So somebody could see the chart, but was not able to hear the sound.
Okay, yeah.
Right. Just let me know that in general, these questions depend whether you open Zoom in browser or download a client. Just wonder, any of you use browser or everybody downloaded a client? Yes, okay, that's a reasonable solution. It takes only a second. I personally always got suspicious if I'm invited for such download. But in case of Zoom, it's practical, it's reasonable. Very good. So thank you for your attention, Sam. I see you on Friday in the same circumstances.
Yeah.
Thank you, Yanis.
Thank you.
I'm ending the meeting. You will be out in a second. Bye.
Bye.